Hello everyone, my name is Sanu and I am student of BSc Chemistry Honors second year. Today I am gonna read metallurgy. So let's start. General principle of metallurgy. Chief modes of occurrence of metal based on standard electrode potentials. The metals are very useful to us. Earth crust is the major source of metals. Seawater is also a source where the metal salts remain in dissolved form. Aluminium is the most abundant metal in the earth crust and the second abundant metal is iron. Metal exists in earth crust in two forms. Metals, native state or free states. Least reactive metals example Au and Pt. Combined state exists in form of compounds. Reactive metals like sodium, potassium, calcium, magnesium, etc. exist as oxide, chloride, carbonate and sulfide, etc. Combined as well as native state. Copper and Ag. Reactivity series of metal are arranged on the basis of standard reduction potential of metals. Standard reduction potential of metals as 25 degrees Celsius are shown in the table. The table shows that from Li downwards, electrode potential get increased accordingly, which indicates the tendency of being reduced gets increased down the series. Thus, below the position of the metal in the reactivity series, greater is the probability of metal to exist as in the free or native state. Thus, the metal lying top in the series are the most reactive and do not exist in the free state at all and exist in the combined form. As we go down the series, probability of finding the metal in the earth crust get increased. So this is a table. And now we will come to Allingham diagram for reduction of metal oxide using carbon and carbon monoxide as reducing agent. Principle of metallurgy. Extraction of metal from metal oxides. Reduction of metal oxide to metal aerospiriting. Reducing agent C or CO. So MO get converts into M. Allingham diagram will tell us which one will be perfect idea for reducing agent C or CO to reduce a particular metal oxide. Some metal oxides get reduced easily while others are very difficult to reduce. In any case, heating is required. MO plus C gives M plus CO, where heat is in positive, so it is endothermic. Study of variation in temperature during thermal reduction is called pyrometallurgy. Gives free energy. The energy associated with a chemical reaction that can be used to do work for spontaneous reaction delta G equals to negative. So T delta S is greater than delta H for a reaction to be spontaneous. Role of reducing agent is to make delta G negative. Some feature of Allingham diagram. An Allingham diagram shows the relation between temperature and the stability of compound. It is basically a graphical representation of Gibbs energy flow in metallurgy. We make use of Allingham diagram to plot the reduction process. Equation. This helps us to find the most suitable reducing agent when we reduce oxide to the pure metals. Let us take a look to some important properties of the Allingham diagram. It is a plot of delta G of O2 versus temperature of formation of oxide. The slope of the curve is the entropy and the intercept representing the enthalpy. Each line of converting metals to metal oxide slope upward because delta G become less negative at higher temperature. Each plot is a straight line except some change in phase, like solid to liquid or liquid to gas. The PT of inflection is the respective line is melting point, boiling point of the metal. The plots are straight line up to the temperature at which the metal remains in the solid state. Large change in the entropy occurs on vaporization of fusion of metals, and thus there will be a change in slope of the lines. For example, the slope of the lines of Hg, HgO, Mg, MgO and Ca, CaO curves change appreciably at 629, 1380 and 1713 Kelvin, which are respectively the boiling point of Hg, Mg and Ca, which increases in temperature. A situation is reached when the lines cross the delta G equals to 0 line. Below the delta G equals to 0 line, the delta G is negative, which means that the heat of formation of the oxide are stable. Above these temperature, the delta G is positive and the oxide will unstable and will decompose to form M and oxygen. This is the situation of HgO and Ag2O, which are unstable and spontaneous, decomposed into the constituent elements. For these oxides, no reducing agents are required to get the metal, which is evident for the self-reduction in the air of cinnamate to obtain mercury. The reaction of metal with air can be generally represented as M solid plus O2 gas gives MO solid. Now when reducing metal oxide, the delta H is almost always negative. Exothermic reaction. Also, since the reaction as seen above, we are going from the gaseous state to solid state, delta S is also negative. Hence, as the temperature increases, the value of T delta S will also increase and the slope of the reaction will go upward. For your understanding, delta S becomes negative, T becomes more positive. So, minus T delta S becomes more positive. In this way, delta G become more and more positive, less negative with the rise of temperature. It indicates metal oxide formation from metal becomes non-spontaneous with the increase of temperature. That means the reverse process. Reduction of metal from metal oxide become easier at a very high temperature. But due to large expense of thermal energy, the extract metal from metal oxide, it is essential to find out suitable reducing agent so that at comparatively low temperature, at low expense of thermal energy, we can extract the desired metal. Industry find out the procedure at which low cost but more production. A Lingam diagram will tell us which reducing agent at which temperature is more suitable for reduction of any metal oxides. Metal that have curves at the bottom of the diagram reduce the metal found more towards the bottom. For your understanding, that in any metal lying at the bottom in the diagram is better reducing agent than a metal lying at the top, as the M lying at the bottom has more negative delta G value for its oxide formation reaction than the M lying at the top. So bottom M will be form MO easily by reducing the top MO. There are the cases where the entropy is not negative and the slope will not be upwards. Let us take a look at few such examples. C plus O2 gives CO2. Entropy of solids is negligible. So here one molecule of gas is resulting in one molecule of gas. Hence there is almost no net entropy, so there will be no slope. It is completely horizontal. 2C plus O2 gives 2CO. Here 1 mole of gas is giving you 2 moles of gas as products. So here the entropy will be positive and the result, this curve will go downwards. 2CO plus O2 gives 2CO2. Here 3 mole of gas is giving you 2 moles of gas as products. So here the entropy will be negative and as a result, this curve will also go upwards. Now we will talk about limitation of Lingam diagram. It does not consider the kinetics of the reaction. Also, it does not provide complete information about the oxides in the information. Say for example, more than one oxide is possible. The diagram gives us no representation of these scenarios. Uses of Lingam diagram. Aluminothermatic process. The line of aluminium on the graph actually lies lower than the most of the other metals such as iron. Essentially means aluminium can be used as reducing agent for oxides of all the metals that lie above in the graph. Since aluminium oxide is more stable, it is used in an extraction of chromium by thermite process. Second, carbon reduction process. C is better reducing agent for ZNO compared to CO. Reduction of ZNO to Zn is carried out at the temperature of 1673 Kelvin. However, it has been observed that above 1273 Kelvin, delta G of formation of ZNO, therefore C can easily reduce ZNO to Zn. Under these conditions, also delta G of formation of CO2 from CO is always more than delta G of formation of ZNO. Therefore, CO cannot be used as reduced ZNO. Below 600 K, only CO reduces FeO. Above 800 K, reduction by conversion of coke to carbon dioxide is spontaneous. Above 900 K, reduction by conversion of coke to CO is spontaneous. Thus, for all reduction of FeO, CO is the better reducing agent below 600 K, but C is better reducing agent above 800 K. So this was all for today. Thanks for watching.